Hello everybody, Mr. Pope from Winter Grammar School for Boys, and today for the Recreational and Competitive Mathematics video number 7, we're going to be looking at some sample British Mathematical Olympiad questions. But when I say sample, I think I can probably get through all 6 of these questions. Although, I just want to talk about the context of what the British Mathematical Olympiad is. When you're in sixth form, typically you know if you're at a good school, and our school does do this. I'm not saying it's a good school, but I'm just saying our school does this. Well, anyway, that's not the point. The point is you'd sit something called the Senior Mathematical Challenge, the Senior Individual Math Challenge that's run by UKMT, United Kingdom Mathematics Trust, and it's usually fairly early on in the year. And depending on how well you score in that, you can move on to successive rounds. You know, you've got various kangaroo papers and all the rest of it, but should you do really well and score particularly highly, then you will get the chance to represent the country at the International Mathematical Olympiad, and you'll also qualify for, you know, a follow-on round called the British Mathematical Olympiad, where all the other smart people that have done really well also qualified for. Now, it steps up quite drastically, I feel. For starters, it's 3.5 hours, the British Mathematical Olympiad round 1, and there's a round 2 for, I believe, is it the top 100? I can't remember. I'm just having a look on the website. The BMO1, yeah, it's up to 100 students who are eligible to represent the UK. Yeah, there you go. So the BMO2, so the top 100 students are following off the back of this, and supposedly it's a bit harder. So I might have a look at some BMO2, British Mathematical Olympiad paper 2s, or round 2, sorry. But there's a couple of other things to take note here. For example, the paper length is much longer. This is to reflect the more challenging questions, and although there's fewer of the questions, you'll need that time because you'll be asked to write full written solutions. And they're quite specific. The marks awarded will be depending on the clarity of your mathematical presentation. Work in rough first and then write up your best attempt. Don't hand in rough work. Complete solutions will gain more credit than several unfinished attempts. So they're trying to encourage you to work on one problem and solve it and move on, rather than having a stab at lots of different questions. And in general, that's, you know, you've got 3.5 hours, that's plenty of time. I say this, so that means each question, what we're looking at, 35 minutes a question. Seems a lot, but I'm hoping I can solve these questions a lot quicker than 3.5 hours. I'm not recording for 3.5 hours. I've got places to be. Each question carries 10 marks. Fine. Use, and this is interesting, the use of rulers, set squares and compasses is allowed, but compasses and protractors are forbidden. That's fine. I mean, it's worth having. To be honest, what I would personally recommend is I would personally recommend bringing in coloured pens or pencils to do the rough working on. The reason for that is, especially with the geometry questions, and you'll probably see when I do them, and just looking at them, I can tell pretty much straight away that question 2 and question 5 are legit geometry questions, and I'm going to need to draw a sketch. And for my rough working, at least, I would definitely be using different coloured pens and pencils, because as clear as my diagram's going to be, I can just tell, because this is a BMO paper, that it's going to be pretty complicated and things are going to go pretty crazy. So that'd probably be my pro tip there. If coloured pens and pencils aren't particularly allowed, then I don't quite see the logic of that. If you can use coloured pens and pencils for your rough working, and then you hand in your best work, but it's all in one colour, i.e. blue or black, whatever it is, then I don't see what the problem is. Start each question on a fresh sheet of paper, write on one side of the paper only. This is just to make marking a lot easier for them. Each sheet working, write down the number of the question in the top left hand corner and your name, initials and the school in the top right. For the purposes of going through this, I will only actually be doing this part, writing the number of the question in the top left hand corner, my name, initials and school in the top right. I don't need to do that going through this exam. Complete the cover sheet provided, blah blah blah. Staple all the pages neatly in the top left hand corner. Okay, yeah, this is all just admin-y stuff. To accommodate candidates sitting in other time zones, please don't discuss the paper on the internet until 8 AM Greenwich Meridian time on Saturday the 28th of November. Okay, so we will have 3.5 hours to do this. I'll set the timer for 3.5 hours, just in case. I really hope it doesn't take me that long. 3.5. Okay, so hopefully this is fairly informative. I want to talk out loud and explain my thought process, how I'd answer it. I'm not claiming to get 100%. I'll try and answer the questions to the best of my ability. I'll check the answers online to see if they are correct. But again, it's this, not just answers are required. You need full written solutions. And to be honest, I'm not going to skip stages in this, so I'm pretty satisfied that I'm going to give full written solutions. Anyway, so let's crack on. Bosh. Right. Okay. On Thursday the 1st of January, Anna buys one book and one shelf. For the next 2 years, she buys one book every day and one shelf on alternate Thursdays. So she next buys a shelf on the 15th of January 2015. On how many days in this period, Thursday the 1st of January 2015, up to and including Saturday the 31st of December, is it possible for Anna to put all her books on all her shelves so there's an equal number of books on each shelf? Okay, I think this is going to involve multiples and divisors. Okay, fine. Well, first of all, let's work out how many days is this. Okay, so let's do stuff. So, first thing. Oh, was that too big? Yeah, probably. Okay, so this is for question 1. So, we're going from the 1st of January 2015, which apparently is a Thursday, up until the 31st of December 2016, which, what was it, a Saturday? Saturday 31st, okay. Right. Okay, general knowledge. In a year, there's 365 days, but 2016 is a leap year because it's a multiple of 4, so that will have 366 days. Just whack that all together. 5 and 6, 1, 6 and 6 is 12. Carry the 1's a 3. So that means there is going to be 731 days. So that answers the first question. So therefore, she's going to have 731 books. But how many shelves is this person going to have along the way? Well, what does it say in the question? She buys one book every day, so it's just the amount of days, and one shelf on alternate Thursdays. So she next buys a shelf on the 15th of January. So that means she's buying it once a fortnight. If there's 52 weeks in a year, then there's going to be 52 fortnights in 2 years, because I just double the years to get double the weeks. So that means she's going to have 52 shelves. And just as a side note, a little bit of working, I've got 731, and I'm going to divide that by 14 days. I want to see how many fortnights are in there. So 14's into 7 doesn't go. 14's into 73. Well, 14, add 14, 28. Another 14 is 42. Add a 14 is 56. Add another 14 is 70, isn't it? So how many 14's in 73? 1, 2, 3, 4, 5. So there's 5, remainder 1. No, have I done that right? Oh, lol, it remainder 3, you silly boy. And then 14's into 31 go 2. And then that's remainder 3, isn't it? So that would make sense. It's 52 fortnights and 3 days remaining. And then if you think about what's going on there, you've got Thursday, let's say of week 1, this is the first, and then you've got Friday of week 1, which is the second, Saturday of week 1, which is the third, the fourth day will be the Sunday of week 1, the fifth day will be Monday of week 2, the sixth day will be Tuesday of week 2, the seventh day will be Wednesday of week 2, eighth day will be Thursday of week 2, 9th will be Friday of week 2, then Saturday week 2, then Sunday of week 2, so that's 10, 11, and the 12th will be the Monday back to week 1 again, if you was on a 2-week cycle, then the 13th would be the Tuesday of week 1, and the 14th would be the Wednesday of week 1, so then they would buy another shelf here on the 15th day, which is the 15th of January, which is Thursday week 1 again. Alternate Thursdays. Okay. So when this remainder 3 is going on, if I was to fast forward 52 of these, then it would be 1, 2, 3, which would be Friday, Saturday. So we would end up on the Saturday. Okay, fine. That's fine. So we've got that. Okay. Right. Fine. Well, this is clearly a periodic cycle. It's going to repeat every 14 days. For the first week, or for the first fortnight, there's going to be one shelf. And then for the second fortnight, there's going to be 2 shelves, and so on and so on. So if we relate that to the number of days, or really the number of books that's going on, then this can be written as, 14 would be 14n, this will be 14n minus 1, this will be 14n minus 2, 14n minus 3, 14n minus 4, 14n minus 5, 14n minus 6, 14n minus 7, 14n minus 8, and so on and so on and so on. And the last term should be 14n minus 13, so that's 14n minus 12, that's 14n minus 11, that's 14n minus 10. And you know what, there's plenty of room here, maybe I should just spread these out a little bit. There you go. Something like that. So, yeah, something like that. This is what's going on. Okay, so on the nth fortnight, she's got these many books. Okay, so when n is 1, so on the first fortnight, she's only got 1 shelf. So really that's saying I can just put any of these books on there and it'll always be balanced, right? As in, I've only got 1 shelf and there's an equal amount of books on each shelf, so because there's only 1 shelf, you know, there is an equal number of books on that 1 shelf. It's just equal with itself. Now when n is 2, what's going to happen? Well, 14n is just 14 times 2. So that's clearly going to be divisible by 2, not only because of the 14, but just because n is a because it's got n in it. So really, it's not going to be divisible by the minus 13, the minus 11, the minus 9, the minus 7 bit, the minus 5, the minus 3, and the minus 1 bit. And the reason for that is because they're odd numbers. You can't divide them by 2. So if I look at the first bit, I just count them as I go along. This is 14. The next bit is 1, 2, 3, 4, 5, 6, 7. What about n is 3? Well, clearly the minus 12 is going to be, the minus 9, the minus 6, and the minus 3, and the n itself is going to be, whereas everything else is not going to be. So that's sorted that out. So it's going to be 1, 2, 3, 4, 5. So there's only 5 of them there. What about n is 4? Well, can we just skip some processes now? I mean, we know that it's this last digit. It's the minus 1s, the minus 2s, minus 3s, minus 4s, minus 6s, minus 7s. It's this last digit that can determine whether it's divisible or not, because the n is always as a multiple, as a factor of 14n. So it's that last bit. So really, you're going to have it from the minus 12, the minus 8, the minus 4, and n itself. So there's only going to be 4 from that lot. And then when n is 5, you're only going to get it from n, the 5, and the 10. So that's 3. And then when n is 6, you're going to get it from the n, the 6, and the 12, which is 2. When n is 7, you're only going to get it from n and 7. So that's 2. And in actual fact, because we've gone over the halfway point of 13, then for n is 8, 9, 10, 11, 12, and 13, these are all going to be 2. So 2, maybe I'll put them over here. So 2, 2, 2, 2. And then, if you think about it, from 14 to 52, it's only going to happen once, right? Because 14 isn't a factor of any of those numbers there, so it's only ever going to balance on that Wednesday of the week 1, i.e. right before she buys a new board. So actually, how many numbers are there from 14 to 52? Well, if I do 52 minus 14, 12 minus 4 is 8, 4 minus 1 is 3, it's 38. But remember, that's not how many numbers there are. There's actually 39 numbers. Okay, you've got to be aware of counting. I mean, think about it. If I asked you how many numbers are there from 1 to 5, I was to count the integers, then there's 1, 2, 3, 4, 5. There's 5 numbers. But if I was to do 5 minus 1, I would get 4. Well, clearly I have to add 1 to that 4 to get the number of digits. So, yeah, just be really careful with that. It's just a counting thing. Fine. So now, actually, I think I've solved this problem. So now, all I have to do is the solution is going to be 14 plus 7 plus 5 plus 4 plus 3 plus 1, 2, 3, 4, 5, 6, 7 2s, so that's 14, plus the 39. Have I done everything? So let's do this in steps. So 14 and 7 is 21, add the 5 makes 26, add the 4 is 30, add the 3 is 33, add the 14, what's that? Have I done this right? Hold on, when is 1? That's 14. This is 14 plus 7 is 21, 21 plus 5 is 26, 26. Oh, lol, I've missed out this 4 here. So for the 4, I would have n minus 4 minus 8 minus 12. Oh dear, that's 4. And then for 5, it would be n minus n minus 5. Oh, oh dear, I think I've shunted these all up wrong. So that should be a 3. I'm pretty sure that's going to be a 2. And for 7, that's going to be a 2 as well. Oh no, I've made a mistake. Okay. Right. So I've actually got 1475, so that's 12 there, plus 14 is 26. So I've got 26 plus 4 plus 3 plus 2 plus 2 plus 2 plus 2. Well, that's a 6. That's a 13. And then 1, 2, 3, 4, 5. That's a 10. So 13 plus 10 is 23. And then I've got to add a 39. So 26 add 39, 23 is 49, plus a 39, that looks to be an 88. I made a mistake here. So I'll let them, doesn't seem... Okay, let me just double check this. I mean, you might as well. You've got 3.5 hours. Let's just double check. I haven't laid this out particularly clear. Okay, so let's deal with an n table, and let's deal with the possible permutations. So when n is 1, I'm going to have all of them, which is 14. Is that right? Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yes. When n is 2, I'm going to get all the even ones, so 1, 2, 3, 4, 5, 6, 7. So when n is 2, I've got 7. When n is 3, I'm going to have the n, but then 3, 6, 9, and 12. So 4 plus 1 gives a 5. And then when n is 4, I'm going to have the minus 4, the minus 8, the minus 12. So 3 plus the n itself is a 4. When I have 5, I'm going to have the minus 5 and minus 10. Plus the extra one, that's a 3. When I have the 6, I'm going to have the minus 6 and the minus 12. Plus the, oh, that was a 3. Whoops, that should have been a 3. Yeah, see, making mistakes. And then when n is 7, I'll have the minus 7. I won't have a minus 14, so that will just be a 2. And then we're over the halfway, so actually... the 8 up to 13, they will all have 2. So 8, 9, 10, 11, 12, 13, that's 6 numbers, so that would be a 12. And then from 14 to 52, they'll all have 1, so that'll be a 39. So let's tidy this up maybe. So I've got a 7 and a 3, which is a 10. I've got a 12 and a 39, which is 40, that's a 51. I've got a 2 and a 3, which is a 5. I've got 4 and a 5, which is a 9. Right. All this stuff up to here is 19 plus 14, which is 33. 5 plus 51 is 56. 33 plus 56 is 89. So the total possibilities, is it possibilities? No, it wasn't possibilities. The total days, so the balancing days. So therefore, the balancing days were 89. Okay, so how would I tidy this up? So let n, so n would be the fortnight cycle and number of shelves, and then for the shelves to balance, you must check the divisibility of n into 14n, 14n minus 1, 14n minus 2, and so on, for n belonging to the set of 1 up to 52. Now, you're probably thinking, okay, actually that's the point. for the last 3 days, no balancing occurs because after fortnight 14, after the 14th fortnight, balancing, well, technically it's after the 13th fortnight. After the 13th fortnight, balancing only happens on the last day of the fortnight. So, since 3 days are too short, don't need to consider them. Okay, full written solution. We've gone through it. 89 days. So the balancing days were 89. There were 89 balancing days. So maybe I should put that this other side. Pardon me. Okay, so my answer and validation would be, well, that's not too bad. It's been 20 minutes. Doing okay. Okay, what's the next one? Right. Let ABC. Okay, fine. Let's start a new page. Question 2. Let ABCD be a cyclic quadrilateral and let the lines CD and BA meet at E. The line through D, which is a tangent to the circle ADE, meets the line at CB at F. Prove that triangle is isosceles. Right, okay, so not a lot here. I think we're just going to have to draw a diagram. I mean, if it's geometric, you might as well. It's always a good idea to do. So, what have we got? We've got a cyclic quadrilateral ABCD. So let's just draw a generic cyclic quadrilateral. This is probably where I'd use different coloured pens. So let's say I've got a cyclic quadrilateral. That is terrible. Lol. I'll tell you what, because it's a cyclic quadrilateral, let's draw the circle first. So let's draw a generic circle in the middle. Then let's say I just draw a random cyclic quadrilateral. Try not to make it like a rhombus or a parallelogram or anything like that, just a general one. If I do it like that, yeah, that'll do. So then, I don't know, let's define this A, B, C, D for giggles. Okay, what else? ABCD is a cyclic quadrilateral that lines CD and BA meet at E. So CD and BA. CD and BA. Okay, so CD and BA, for them to meet, that would have to extend like that. And BA would have to extend like that. And this is where E is. Could it be possible that... Is it possible for E to be inside the circle? Maybe it is. I don't think it matters so much. Don't think. Okay, well, we'll get to it. The line through D, which is tangent to the circle. Hold on, the line through D, which is tangent to the circle ADE. Oh dear. Okay, ADE. Oh wow. ADE. I've got to draw a circle that's... Okay. Different coloured pen. Let's draw a circle. Okay, so I'd actually use a compass to do this properly. but I want a circle that goes through A, D, and E. So it's going to look like something like that. A, D, E, something like that. Okay, is that what it wants? It wants the circle ADE. The line through D, which is a tangent to the circle ADE. Okay, so I need to draw a tangent to that circle ADE. So here's my tangent to that circle. Let's say it's a line looking like that. Mate, really? So there's that. It's not looking that good. Okay, let's draw a line like that from there to there, maybe. So there it is. That's my tangent through D. Something like that, maybe. So that's the tangent to the purple circle. Meets the line CB at F. CB. Oh, okay. Oh, wow. Okay, it's going to be all over here. So that means if I draw CB like that and just keep going like that, I draw this blue line, I keep going. Wow, I've not done this particularly well. They're not parallel, so they would meet eventually. Lol. Oh, man. Well, it's not a problem. Maybe let's, for artistic impression point of view, let's say the tangent looks a bit more like that. That goes like that there. And, you know, let's take this and shrink it down. Let's have this really small. This will carry on going like this, say, and then this will carry on. It's probably a better way of drawing this, but I'm just doing it for the giggles. And apparently this point over here we call F. Is that what that's saying? So that tangent thingy, so it meets the line CB at F. Prove that CDF is isosceles. CDF. Okay, so if so they want CDF is isosceles, you want to prove that that angle is the same as this angle. Okay. Right. Gotcha. Okay. Right. So, if we call this angle, let's call it X. What else do I know? Well, I know that angles in a cyclic quadrilateral are supplementary. They add up to 180. So this must be 180 minus X. I know that angles in a straight line add up to 180 minus X. Mate, what's going on? Okay. Oh wow, actually this is... Really? It can't be that easy. No. Wow. Okay, yeah, okay, fine. Actually, yeah, that's easy. Because now, this angle here is 180 degrees minus x, because you've got a triangle, ADE in the circle, and by the alternate segment theorem, this angle is the same as this one. And then since angles on a straight line are up to 180, this angle here must be x, as in this big angle here. And then therefore you've shown that the angle there is x, the angle here is x, and you've got the triangle FDC is isosceles because it's got two base angles the same. Okay, yeah, that's quite easy actually. Good diagram. So let's talk about this. Why is it? Well, okay, let's talk through the logical steps. Suppose the angle BCA equals to x. Then angle BAD equals 180 degrees minus x because of opposite angles in a cyclic quadrilateral are supplementary, i.e. sum to 180 degrees. This then I don't know, let's call, what letter haven't we used? Let's call G over here. Then we have angle EDG equals 180 degrees minus x because of the alternate segment theorem. It is the same as angle BAD on the circle ADE. Yeah, no, that's legit because A and D are on both circles, so that's fine. Yeah, that's totally fine. And then angle EDF equals x because angles on a straight line sum to 180 degrees. So 180 degrees equals angles EDF plus angle EDG, and 180 equals angle EDF plus 180 degrees minus x. So yeah, that's it. And then we have, since in the triangle CDF angles FCD. Oh, what am I saying BCA? Lol, BCA is not a thing. You silly boy, it's not BCA, it's BCD. It's BCD is X. Yeah. Okay, since the angle FCD equals the angle BCD, and angle FCD equals the angle CDF, then triangle CDF is isosceles because of two base angles the same. Yeah, wow, that was incredibly easy. Yeah, that's pretty much what I'd write for that one. Maybe I can expand this. Yeah, something like that. That's what I'd write. So yeah, that actually wasn't too bad of a question. A lot easier than I thought it was. I mean, this one was quite easy as well. Yeah, a third of the way through, plenty of time. Okay, let's tackle question 3. Oh dear, let's make it a bit thicker than that. Let's have question 3. Suppose that the sequence T0, T1, T2 is defined by the formula T of n equals that. Okay, this is quadratic. Fine. For all integers where n is non-negative. Here, a, b and c are real constants with a not being 0. Determine the values of a, b and c which give the greatest possible number of successive terms of the sequence which are also successive terms of the Fibonacci sequence. And then the Fibonacci sequence is defined by blur as follows. Okay, so let's remind ourselves of the Fibonacci sequence. So really, we're comparing, what we're doing is we're comparing a that's a capital F, a Fibonacci sequence with a quadratic sequence. Now for a n squared plus a plus bn plus c, the only thing we know about that is the second common difference is 2a. Remember? Because if I take a quadratic sequence and I find the second common difference, then whatever the second common difference is, I halve it, and that gives me the coefficient of n squared. So really, the only thing, so I'm going to recall that. So recall that with a quadratic sequence, the second common difference is 2a. For a quadratic sequence, that for n squared plus bn plus c, which, by the way, this is t of n, right? The second common difference is 2a. Okay, for a Fibonacci sequence, what do we have? Okay, so the first term they defined as 0, the second term they defined as 1, and then you add these two, so the next one's a 1, the next one you add 1 and 1 together to make a 2, then 1 and 2 together to make a 3, then 2 and 3 to make a 5, 3 and 5 to make an 8, 5 and 8 to get a 13. I think that's probably enough. So, shall we have a look at the second common difference for this to work? So 0 to 1 is 1, 1 to 0, 1 to 1 is 0, 1 to 2 is 1, 2 to 3 is 1, 1 being silly, 3 to 5 is 2, 5 to 8 is 3, 8 to 13 is 5. Then if you look at it, it's just going to be minus 1, 1, 0. And then it looks like it's just going to be the Fibonacci sequence again, isn't it? That's interesting. Look, because it's just so. If I was to do this one more time, I don't know. Let's check it. It's not something I want to prove, to be quite honest. 8 plus 13 is 21, and clearly that's going to be a difference of 8. And then 5 to 3, yeah. Okay, so clearly, the differences of the Fibonacci sequence behave like a Fibonacci sequence themselves. And to be honest, you could probably say, well, actually, these are the Fibonacci things as well. Because if you think about it, 1 add 0 is 1, 0 add 1 is the next one. And yeah, so really, these are just Fibonacci sequences themselves. This is a bit dumb. Is there any point in time? Well, there's no point going back before here, because it says the Fibonacci sequence is defined when m is greater than or equal to 2. Or rather, this rule only works for m is greater than or equal to 2, so we can't really go back from that. Oh mate, what's going on? So really, apart from the initial term and then the initial two terms, it's just this and onwards. So we can't... The point is, there's only two terms in the Fibonacci sequence that are the same. And that is clearly going to be when the second common difference is 1. So the second common difference of 1 can, equates to these three terms in the first common difference. So that equates to these three terms here, 2, 3, 5, and 8. Okay, so we need a sequence where it goes 2, 3, 5, 8. Now, right, I know that this is when n is 0, 1, 2, 3, and this is when n is 4, and this is when n is 5, this is when n is 6. But it says, suppose that T0, T1, T2 is defined by that formula for all integers, blah, blah, blah. Here A, B, and C are real constants, blah, blah, blah. Determine the values of A, B, and C which give the greatest possible number of successive terms of the sequence, which are also successive terms of Fibonacci sequence. Okay, so what I've actually done is these aren't n is 3, this is m is 3, this is m is 4, this is m is 5, this is n is 6. I now want to turn this over, so now this is n is 0, this is n is 1, and this is n is 2, this is n is 3. And now I want to equate these to my Tn formula. Well, when n is 0, I've got a lots of 0 squared plus b lots of 0 plus c. So it looks like c is just going to equal to 2, so that's nice. Next up, we already said the second common difference is 2a. Well, if 2a equals 1, then a equals a half. So actually, we're nearly there. We've got c, we've got a, we just need to work out b. And so we can do that quite easily, right? We can just sub in n is 1. So we've got 1 squared times a, which is a half, plus b lots of 1, plus c, which is 2, equals to 3. Why did I do that? C is 2. Have I done this right? I feel like I'm missing something. Did n start at 0? Am I being silly? Yeah. Well, I'll tell you what, if I've made a mistake, we'll just sub it in and see how it goes. Okay, when n is 1, I've got 1 squared, which is 1, times a, which is a half, so that's a half, plus b times 1, which is b, plus c, which I worked out is 2, equals, when n is 1, it needs to work to 3. Okay, so 3, okay. So I'm saying b equals a half. So is it true that Tn is a half n squared plus b, which is a half of n, plus c, which is 2? Does that make sense? Well, so for n is 0, it works. For n is 1, I've got a half of a half. I've got half of 1 squared plus a half of 1, so that's 1 plus 2 is 3. Makes sense. Now what about for n is 2? Will this work? Well, 2 squared is 4, half of that, plus a half of 2 plus 2. Well, half of 4 is 2, plus half of 2 is 1, plus 2 is 5, so that seems legit. Let's check when n is 3, so I've got a half of 3 squared, which is 9, plus a half of 3, plus 2. Right, 9 halves plus 3 halves is 12 halves, which is 6, plus this 2 is 8, which is what I wanted. Bang. Okay, so Tn is the following. And you need to say, therefore, there are no other consecutive terms in the Fibonacci 1b Fibonacci sequence that are the same apart from 1, 1. So that has to be the result. This is just check, you don't need that. Cool. Okay, so that's question 3. So halfway through, and we've spent half an hour. Coolsies. Right, where are we now? Question 4. Start a new page. Let's pick a different colour. Let's go for purps. This is question 4. Okay. Question 4. James has a red jar, a blue jar, and a pile of 100 pebbles. Initially, both jars are empty. A move consists of putting a pebble from the pile into one of the jars or returning a pebble from one of the jars to the pile. Okay, so that's like a counting game. Okay, fine. The numbers of pebbles in the red and blue jars determine the state of the game. Okay, interesting. Fine. So it's not necessarily how you get there, it's the fact you've got there. Okay, the following conditions must be satisfied. The red jar may never contain fewer pebbles than the blue. Okay, so the blue must be equal or less. Fine. And the game may never be returned to a previous state. Interesting. What is the maximum number of moves that James can make? Okay. Right. So. Okay. Let's just deal with this. So, hold on. Let's deal with the problem in general. Let's create a little table, and let's say going along the top are my reds, say, and going along the side down here we'll say are the blues. So I've got 100 pebbles, so really I need to consider all the cases where 1, 2, 3, 4 goes up to 100. And with the blues, I need to consider 1, 2, 3, 4 going up to 100. But there's a couple of things I can do here, I think. Let's have that out. Let's have that down there. Let's have you there, you there, you there, you there. Okay, for a start, I can't have more in the blue than in the red. So what would that mean? So I can't have the space where blue is 2 and red is 1. I can't have the space there. I can't have that space there. And I can't have this space here. And so on. I can't have this diagonals of stuff going on. Okay. What else? Is that what, hold on, what were the rest of the rules? The red jar may never contain fewer pebbles than the blue jar, and the game can never be returned to a previous state. There's only 100 thingy bobs, right? So, that's interesting. You're never going to have. Okay, so is the constraint because blue must be less than or equal to the red pebbles. Okay, next up, we can't have anything in there, and so on and so on and so. We can't have anything in there. We can't have anything in this column. Oh no, we can. Oh man, I've forgotten the zeros. I'm such a mongrel. Right, okay. I need to back it up a little. No, let's just back it up. Okay, no, actually, to be fair, it's just a counting problem. Let's just go back. This should now make sense. I've got 0, 0 here. I've got 1, 2, 3. And I've got 1, 2, 3. Yeah, that still makes sense. I can't have, yeah. And I can't have any of these things down here. Can't have any of these. Can't have any of these. Now, actually, I can have this red one because it is possible for me to have 100 red and no blue because there's 100 counters. But then similarly, you know, this is going to form some kind of pyramid-y thing going down like that. That's interesting. So there's going to be some kind of it's almost like you've got a block like that, and then you've got a block like this, and then a block like this, and a block like this, and a block like this, and a block like this. And they've all got an overlap of 1 on each side. You've got like, okay, I see. Well, you start here, right? You start here. 0, 0. You can't go down into the 1, 0. You can't put. The reason you can't do that is because you can't put 1 in the blue. So then, okay, so your first step is you have to go into this block here, where you've got one red counter, and no blues. Okay. What else can you do? Well, you've got a choice of either going down or to the right. If you went down, then your only choice left is to go right, because you can't go back into a previous state. And then if you're to the right, you've got a choice of going up or down. If you went up, that's going to meet as if you'd just gone there. And if you were in there, you could have gone down. So these two you probably could have gotten. Is there a logical way to explain this? Well, let's suppose I just ran straight all the way along. Could I do that? Could I go into the 100? Well, no, I couldn't, because the only way to get out of that box is to take one red pill out, and that would go to a previous state. So in actual fact, I could do all but 1 in that row. So I'd go all the way to there. So I'd have 99 moves, would I not? No. I'd have 100 moves. Start at 0, 0. And then there's the numbers 1 to 99. So yeah, no, I would have 99. I'd have 99 moves here. And then what I'd do is I'd then put 1 counter in the blue bit, that final blue bit, like so. Right. So I've got 99. No, sorry. I wouldn't do that. I'd go to the 99 and 1 back over here. So here's the 99 column. What would I do now? Well, this is the interesting bit, isn't it? Because if I go back along a square, then I've done 2 moves. Have I not? Because I've taken one out of the red and put it into the blue. So every time I move a square across, that's 2 moves. I take one out of the red and I convert it into the blue. So if I go all the way to the edge and I stop here, because I can't go there because I can't go back to here or here, so that one's out. So hold on, the red stuff indicates, what's it? That indicates total must be less than or equal to 100. And the green stuff is it would force a previous state. So I can't go in there because that would force a previous state, and I can't go into there because that would force a previous state. So how many moves would that next row be? Well, it's going from 99 to 2. Well, oh man, why is this being so slow? James has a red jar, blue jar, and a pile of 100 pebbles. Initially, both jars are empty. A move consists of moving a pebble from the pile into one of those jars or returning a pebble from one of the jars. The number of pebbles in the red and blue jars determine the state of the game. Okay. I think I get it. So for the first round, because they're all out in the pile, you can just keep adding them to the red jar. So that'll just be it. It'll just be 1 lots of 99. However, to go from 99 to 2, 99 minus 2 is 97. So that means there'll be 98 moves. But because because you're taking you're initially putting 1 into the blue, the final one, the 100th one. And then you use another move to take it out, so it's 98. Oh no, and you're just taking them out of the red, so it's not doubling. No. Yeah, no, you're not doing 2 moves, are you? You just, when you're in that row, you're just taking stuff out of the reds. Oh man, this is a mind mess. Okay. So you go 1, 2, 3. So there's 99 in the first row. And then to get into the next one, you do 1. Yeah, no, this is just 99. Is there 98 there? Mate, what's going on? 98. Is that true? Yeah. Because we're going from 99 back to 2. In the reds, we're going from 99 back to 2, so it's going to be 98 steps back. And then, okay, suppose we're here now. Then I'd put 1 in the blue, like that. And then I'd keep zigzagging along, and there'd be 1 I couldn't get to because it would be like that, which would be at the 98th, 100th, 98th, so it'd be the 98th. So I'd go from 97. So I'd only be allowed to go from the second. So 98th minus the second is 96, so it'd be 97. Ah, it'd be 97. Oh, that's interesting. So it's like a decreasey thingy. Okay, so you'd have 99 there, 98 there, 97. The question is, how long does this keep going down? Well, okay. The top row is from 0 to 100, which is 101. And then it gets two smaller. So then it goes 99, then 97, then 96, and so on and so on. And the bottom one is 1. So if the first row, if you like, from the bottom is 1, then what's the nth row? So that's 101. Well, oh, that's 97, that's 95, isn't it? So it's actually 2n minus 1, isn't it? So I have two lots of 1. So if this is when n is 1, two lots of 1 minus 1 is 1. So two lots of what minus 1? Is that 51? Two lots of 51 is 102, minus 1 is 101. Okay, so it's 51 rows. Ah, would it just be easier to do that then? Because I'm always having to subtract one anyway, because I can't do this zigzaggy loop type thing. So it will be the sum from 1 plus 2, not 2, it would be 1 plus 3 plus 5 plus so and so up to 99 plus 101. And there's 51 of these things. But then I have to minus, so the total, the total amount of moves is going to be the sum of the whole things, but minus 1 plus the number of rows, because we have to minus 1 because of the start, but then the number of rows, because there's these green squares that we can't have. So that's going to be 51, isn't it? So it's 51 rows. Oh, is that right? I think so. Okay. Well, this is definitely right, the number of rows in this upside down pyramid thing. So Sn is just going to be so 51 times by 51 plus 1, which is 52, over 2. Yeah, because n times n plus 2 over 2. No! Oh my god, that's for numbers. Stop it. So Sn is n over 2, so 51 over 2 times by 2 lots of A, well that's 2, plus n minus 1, which is 50 lots of 2. Okay, so it's going to be 51 all over 2, then 50 times 2 plus 2 is 102, so the 2's cancel, so it's 51. Oh, it's 51 squared. And 51 squared, 1 times 1 is 1, 1 times 5 is 5, 0, 5 times 1 is 5, 5 times 5 is 25. So that, and that, and that, and that, and that, and that. Right. So there is 2,601 squares. Oh, yeah, no, you're not going to... there's 51 rows, but you're going to be able to like get into this final one, so you're not going to... Aha! Yes, that's what's going to happen. So the total is going to be that. So this is clearly going to be 2,601 minus 51, which is 2,550 moves. Okay, so to tidy this up. Yes. So how would I describe this? So right, first of all, this is all rubbish. I wouldn't have this. Okay, this is kind of rough working. I'll put this over to here. So so what would I write? So okay, this is probably the lamest part. So consider a board mapping the states of blue pebbles and red jar pebbles as seen above. I should put a jar in here and squeeze that over. Oh, mate, come on. Well, okay. It's not playing ball. Okay, so consider a board mapping, a board mapping the states of blue jar pebbles and red jar pebbles as seen above. The initial starting square is 0, 0, and moving from one square to the next counts as one move. For example, going from 1, 1 to 1, 2, from 1 should be 1, and that should be an adjacent square to the next counts as one move. So 1, 1 to 1, 2, well, that's 2 going downwards, means you're adding a blue pebble. Okay. Next, consider the region. So really, I need to write this stuff down in words. So I do this. So let B equals pebbles in blue jar, and R equals pebbles in red jar. Then consider that stuff and stuff and stuff. We now have a feasible workspace which appears to be an upside down pyramid with 51 rows containing, what was it, 2,601 squares. Since backtracking is not allowed, it is impossible to visit both end squares of each row, and in fact the first top row, no, that's fine because we started at one of them. So notice that the 51st row is the final destination, so that is ignored. So 2,601 minus the 50 minus the 1, and this indicates the total squares minus 1 square from each row, not the last, and this one here is the starting square, and this equals 2,550, and this is the maximum moves. Cool. Yeah, quite tricky. Just to make this a little bit nicer on myself, make this a little bit, oh, whoops daisy. Something wrong with my iPad, it's really playing up these, mate, come on. There you go. Cool. Yeah, tricky question. Still got 2 hours 20 left. Where are we now? So we've done the first 4 questions. Let 5, lol. 5, let A, B and C be a triangle. Okay, fine, let's just draw that. That's easy enough. I can just draw any kind of triangle. And for giggles, let's use purple. I'm going to draw a nice large triangle. So, bosh, bosh, bosh. No. Oh dear, whoops, let's do that. Let's make it, scalene, something like that. And for giggles, stop it, let's call this A, let's call this point B, and let's call this point C. Let D, E and F be the feet of the perpendiculars from A, B, C to the opposite sides BCCA and AB respectively. Okay, so when we take the per foot, what does that mean? So that means if I draw perpendicular from A to BC like that, so I get it roughly looking like 90. So that's 90, then this is D. If I draw a perpendicular from B to C, so that's as close to 90 as possible. I don't know, looking something like that maybe. And then C drop down to AB like so. That should have been there. Now that's not good. I've drawn a very bad diagram here because the perpendiculars, when they drop down like that, it's a special thing of a triangle. I always forget, I think it's called a centroid. I'm not sure. It's a special property. Yeah, it's important. It's not where the centre of mass is, and it's not the centre of a circle that spans out the triangle, but it's important nonetheless. So this was point E, wasn't it? And this was point F. Okay, I think I've done that bit right. Okay, the point is they should all meet at the centre. You should be familiar enough with the point where the perpendicular, the feet of the perpendiculars. Anyway, the perpendiculars should all meet that point. Let P, Q, R, and S be the feet of perpendiculars from D to BA. Okay, so how do I go from D to BA? D to BA. Okay, so let's draw D to BA. It's looking like that. Let's draw it parallel. So that's 90. This is apparently P. That doesn't look accurate, but never mind. D to BE is Q. BE, 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 D to BE. Okay, so that's going to drop down looking like that maybe. D to BE. That's Q. D to CF is R. CF. CF. D to CF. Okay, so that's going to be popping out like that, kind of. Mate, what's going on? D to CF. Looking a bit like that. That's R. And then D to CA is S. D to CA. Okay, so that's going to be like that somewhere. That's S. Okay. What's the question want me to do? Prove that PQRS are collinear. Okay, so they all lie on the straight line. So if I've done this correctly, I should have a straight line going through P, Q, R, and S. Something like that, maybe. I've not drawn this particularly well, but you get the idea. Do you know what? I'll put like a solid dot there. Okay, so prove they're collinear. Okay. Right. So, boy, how are we going to tackle this? Well, I tell you what, is there anything that's parallel with that line? PQRS. Well, CB looks like it would be, but then, yeah, I just feel like we could drag B off into that direction. And although D might lift up slightly, that wouldn't affect this line too much, so I don't think C to B seems parallel to me. Well, it's definitely not parallel with anything else. The only thing could potentially be parallel with is this thing, F to E. I mean, it could be. Kind of looks it. Well, F to E is something. Let's just say that that's a thing. And we don't know that PQRS are all collinear. So what we're going to have to do is we're going to have to break up RS. We're going to have to break up that segment RS. So this is RS. We're going to have to break up this segment QR. I probably shouldn't use purple. QR. Let's break up QP. And then let's have the final section EF. This little, what's it called? A section? Section of a line? Yeah, section of a line. I'll take it section of the line. Okay, EF. Right. Okay. Right. There's lots of 90 degrees popping out here. There's not a lot we can do with them. Okay, what do I know about 90 degree things? Well, actually, I could create circles, couldn't I? Why would that be useful? Well, yeah. No, I could do that. Okay, fine. I'm going to imagine creating a circle, right? Because I know this is a 90 and this is a 90, and both of the 90s kind of point down to A and B. So this actually looks like a cyclic quadrilateral. So what can I tell straight away? That consider the cyclic quadrilateral AEDB, where AB is the diameter. Then what are we going to get from that? Well, we're actually going to get that this angle is the same as this angle because of that theorem of this theorem. You know, if I've got 2 points like that and I've got these other 2 points there, if I do that, and then that, then that angle is the same as that one. I forget what it's called. So I'm just going to draw it like that. So what have I got? I've got angle EAD equals angle EBD by what's it called? Circle theorem, and it's subtending. It's angle subtending the same arc. Yeah, it's angle theorem. Angles subtending the same arc. Yes, okay, they're similar. What else can we say is similar? Well, we can also I want to get some similar triangle things going down. Okay, fine. Let's call this point in the middle where they all meet. Let's call that X. I also know that let's call this angle here. This is the same as this big angle here, and the way we'll write that is angle EXF is the same as angle CXB, because of opposite angle or vertically opposite angle theorem. Okay. Now I feel like I can play this stuff again. There's got to be another cyclic quadrilateral going on here. Yeah, there's another cyclic. I mean, pretty much anywhere where there's two 90 degrees, I can tag them up. So, I mean, there's a 90 degree here. Where else is there a 90 that could go with it? No. Where did I find the last one? AEDB. AEDB. Yes, they weren't necessarily on them. Where would a good cyclic quadrilateral be? Well, put it this way: we let AB be the diameter. Oh dear me, we let AB be the diameter of 1, right? So how about we consider the cyclic quadrilateral where not AB this time, but let's pick another side. Let's try BC. Well, I've got a 90 degree there and I've got another 90 degree there, so it could be BEFC, BFEC. Like that. So consider the cyclic quadrilateral BFEC. So if I just did that for a second, what's going to happen? Then I don't know if you can see, but then that means that this angle is the same as this angle. So then, that means that the angle Angle, what is it? ECX. ECX equals angle FBX. For similar reasons up there. So angles subtended by same arc. There's actually a couple of things going on here. What do I mean by that? Well, you're going to have this angle is the same as this angle because they're vertically opposite. So you're going to have angle CXE is the same as the angle FXB because they're vertically opposite. And you're also going to have the triangle CEX is similar to triangle, and now you've got to get this right. We're going CEX, that's BFX, because three angles are the same. Okay, so I've proven that. What have I done? I've proven that this triangle is similar to this triangle. Okay. In actual fact, could I have not have done that elsewhere? So I've A, B, B, C. There's one more triangle, isn't there? There's another cyclic quadrilateral I can consider. There's the cyclic quadrilateral, where we start at A, finish at C. And where's the two 90s I want? There's one at F, and there's one at D. So it's AFDC. AFDC. So I've got the cyclic quadrilateral AFDC. You know what, I'm going to move this stuff to the side, like so. So in the cyclic quadrilateral AFDC, it's a little bit difficult to tell. If I do it larger, I've got AFDC like this. Imagine these are on a circle, such that that's kind of going around like that. Like that, say. And that's allowed because that's a 90 there and that's a 90 there. Then clearly these two angles are the same. So let's get rid of all this. Okay, so let's change this to blue, say. Then this, oh dear. This angle is the same as this one. Okay, so what's that? XCD or FCD. So angle FCD equals angle. There's a lot of symmetrical arguments here, and then FAD. FAD? FAD, because angles subtended in the same arc. Okay. Right, what else can we do? If they're subtended in the same arc. I feel like there's way more cyclic quadrilaterals. Geez. Okay, right, fine. So, do you agree that there's a 90 here and a 90 there? because if that's a 90, that's a straight line. So actually, oh man, we've got a mini cyclic quadrilateral there as well. Oh geez. Wow, we're gonna have tons of cyclic quadrilaterals popping out here. I think that's going to be the key actually. So we're going to have a cyclic quadrilateral. What is it? CSRD, such that, if you think about it, then that means this must be the same as this angle. Ooh, interesting. Interesting. So that means angle SCR equals angle SDR, because of angles subtended by the same arc. Okay, I'll tell you what I'm going to do. I'm going to shrink this down so I've got a little more space to play with. Oh mate, come on. Mate. Okay, actual fact, I can probably bring some of this stuff up. Bring that. Oops, a daisy. Okay, and in that quadrilateral, is there anything else? Ooh. Well, I've also got this angle is the same as this one. Have I used green before? No, I haven't. So that means I'm going to have angle C. Well, they're just vertically opposite. Yeah, I don't need to say that. They're vertically opposite. So that actually means triangle, if I call this Y, then triangle CSY is similar to triangle DRY. Dry. Okay, how does that help? Cannot do something else like that. Well, in actual fact, and then I've got another cyclic quadrilateral, and this time it's DB, so DQPB, where DB is the diameter, and then I'm going to have that, what am I going to have? Oh, I'm going to have this angle. Ooh, I've got angle QDP is the same as angle QBP because of angles subtended by the same arc. Okay. Oh man, there's so many similar triangles going on here, isn't there? What else can I do? Those two angles the same, those two angles the same. if I call this Z, say, then clearly this and this are the same. So angle DZQ equals equals PZB because of vertically opposite angles. What have I got now? Oh, I must have some things going on here. Oh yeah, that's what I haven't taken into account. I haven't taken into account that this line is parallel with this one, and I haven't taken into account that this line is parallel with this one. Oh man, I'm such a wally. So much here to do. So, okay, first of all, let's copy this stuff and put it down at the bottom. Okay, so what can we say straight away? Well, we can say a few things. We can say that that this angle is the same as this angle, because angle DPR equals angle FRP because of alternate angles. That's fine. And then this angle is the same. So angle FRP equals the angle SRC because vertically opposite. That's fine. And then I think that's nice because now triangle CSR is similar to triangle C, is this that one? Lol, DPQ, because same angles. So yeah, that's fine. What else can we piece together from this? No, I don't know. It's FRP, do I? I shouldn't be really using P, should I? I should be saying FRQ there. And DPR, I don't know if that's, that should be DPQ equals F. Oh, do I even know that? No, I can't say this. I can't say this, sorry, this is bad because I'm assuming they're a straight line. That's not cool, can't do that. That's bad logic, bad me. Okay, so actually I don't know if these are the same as this. No, I can say that these two are the same because they're vertically opposite. So actually I can still say that SRC is the same as the angle FRQ because they're vertically opposite. No, that's fine. But then are they necessarily the same? Wow. That's throwing a spanner in a few things. Let's have a pause and think. Right, sorry about that. I've been out. Okay, so where were we? Right, couple of things. Okay, so actually, have I said anything about triangle CEX? Yeah, I have. Okay. Well, how about this? How about triangle? I really need to know that angle, really. Okay, no. How about triangle CSY is similar to CEX because of same angles. So then actually I can replace these with a green colour. So that's fine. So what I'm saying is this triangle is similar to this bigger triangle here, because they share that angle in common. They've got 90. Okay. What else could I prove? I really want to show that triangle CSR is similar to triangle CEF, because then if I can do that, then S to D is parallel with E to B. Then S to R is a parallel with E to F. I've got the triangle CSR anywhere. No. Okay. Well, what did I do with the AC? Come on, man, these things are really tricky. There's just so much going on. Cyclic Quadrilateral AC. That was here, wasn't it? AFDC. AF. Okay. Wait a minute. If AFDC, then these two are the same, which makes sense. Those two are the same, which makes sense. No. Wow, interesting. Right, I think what the argument needs to be is that this is 90, and what you've got here is this, so you've got the shape, which is CSDRC again, which is CSRD, is similar to CEB back to F, then to C again. CEBF, it's similar to that. Those two shapes are similar. So shape CSDR is similar to CEBF because it's two similar triangles, pairs, and also since CS is on CE and CD is on CB, that means that F to E is parallel with R to S. Okay. So if that's parallel, then maybe I shouldn't have used pink here. Let's use a different colour. Let's use brown for this. Then if I know that's parallel, then immediately I know that CRS is parallel with this. And I know that this angle here is the same as this one. And since I know those two green ones are the same, then this is the same as this, which is the same as this thing down here. And that's because DS is parallel. Which now means that this has to be orange, because you've now got a pink and a brown, which is the same as a pink and a brown there. And that orange there must mean that's orange there. And if that's the case, then you have alternate angles there. So because of alternate angles F, E, X, Q, R, that must mean that FE is parallel with QR. Now I think a funny thing's going to happen, Because if you think about it, this was the middle section. This was one end, and this was the other. But if you turn this on its side, the same argument for this thing must be the same argument for this. We can probably prove that actually. But just by symmetry, it's going to work out that way. Because if you think about it, this D point there is splitting the triangle like that down there. And you've got similar shapes going on. You know, you've got this bow tie thing here versus this bow tie thing here. So I would argue, therefore, because of symmetry, argument for P to Q being parallel to FE follows from R to S being parallel to F to E. But now, if RS is parallel with QR, which is parallel with PQ, which is parallel with FE, then PQRS is collinear as they share points and are parallel. Cool. Right. Oh mate, what's going on here? Right. I think that'll do for that one. Oh mate, what's going on? Okay, question 6. A positive integer is called charming if it is equal to 2 or it is of the form 3 to the I or 5 to the j, where I and j are non-negative integers. They could be 0. Prove that every positive integer can be written as the sum of different charming integers. Right, so this is question 6. Okay, so let's think about this. So let's call the charming numbers C with this thing here. Well, first of all, what's the set of the charming numbers? Well, 1's in a charming number. Well, okay, I'll tell you what. We know that 2 is a charming number, and now let's write a table of 3 to the 0, 3 to the 1, 3 squared, 3 cubed, 3 to the 4, and so on. And then let's write 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3, and so on. This way, if we do it this way, we know we're not going to miss any pairs as we build up initially. So 3 to the 0 times 5 to the 0 is 1. And then to fill out this row, I just times everything by 3. So 3, 9, 27, 81, and so on. And then I times it by 5. So 5, 15, 45, 27 by 5. 7 5s are 35. 2 5s are 10, plus that is 135. 81 times 5 is 405. And then we carry on. Times by 5 is 25. Times by 5, 75. Times by 5 is 25, 5 4s is 20, it's 225, times by 5 is 25, 5 3s are 15, plus the 2 is 17, 675, and times this by 5 is 25, 4 times 5, that's 20, 25, and so on. So we now have a multiplication table. So we've got 1, 2, 3, 5, 9, so we've done that one, that one, that one, 9, then 15, then 25, and so on and so on and so on. Now, I want to be able to express every number as the sum of charming numbers. Okay, well, so if I write my numbers, let's say n, then, well, 1 is easy, that's just 1, because 1 is a charming number. 2, that's a charming number, so I'll write that as that. 3 is a charming number. 4, well, the 2 charming number, I can't have 2 and 2 because they've got to be different, so I'll have 3 and 1. 5 is a charming number, so I'll just write that as 5. And to be honest, is this unique? Is there more than one way of doing this? Well, no, with 5, I could have had 2 and 3 because they're both charming as well. So there isn't a unique way of doing this, I don't feel. And I think the rule will play is if I can use a charming number, not charging, charming. If we can use a charming number, I will. So 5 will be used over 2 plus 3 just because it can be, although 2 plus 3 is valid. 6, I can't have 3 and 3. I could have 1 plus 2 plus 3, that's 6, or I could have 5 plus 1. And in this case, I'll probably choose the 5 plus 1 case, just because it's fewer. So the other stipulation I'll have is I'll choose less numbers. Okay. Is it possible to carry on doing this? Well, couple of things. I notice it's got the numbers 1, 2 and 3. And I notice if I double, well, okay. See, look, if I double 1, I'll get 2. So that's fine. If I double 2, I get 4. But I guarantee there's a charming number before that. If I double the 3, I get 6. I've guaranteed a charming number before that. If I double the 5, I guarantee a charming number before it. If I double the 9, I'm going to get one before. Double the 15 before. Does this hold? Okay, so first thing I'm going to say is there, for any n where n is a charming number, a number such that n plus, let's say some a, where a is less than, well, it's greater than or equal to 1, but it's less than n, is also charming. So is it possible that I can add some amount to n? And also, by the way, if this is charming, n is charming, can't spell charming, Jesus, charming, then it's its own sum, and then a is some other number which can be arbitrarily written as a sum of charming numbers. So what we're going to do is we're going to start off something called proof by induction, where we're going to do it in blocks. So yeah, I think that's probably the best way actually. So for any n, as long as I can prove that if there's any n, yeah. So, okay, fine. So what is n? Well, clearly, when n is greater than 2, n is always of the form 3i times by 5j, right? Okay. So for n is greater than 2, n is of the form 3i 5j. Cool. So if I was 0, what's going to happen here? Well, if I was 0, this has to be positive, non-negative. So if I had 3i plus 1, and then this is some 5j. Is that going to work? No, what am I trying to say here? Well, okay, if I was naught, then I think there's something else. I want n is greater than 2, so that means j is going to have to be greater than or equal to 1. Because if j was it, they can't be negative. And they have to be integers, so j has to be greater than or equal to 1. So that means n can be written as 3 to the I plus 1 times by 5 to the j minus 1. Yeah, because it's going to be some 3, and the lowest 5 you can times it by is 5 to the 1, 5 to the 0. But j has to be greater than or equal to 1. Yeah, yeah. So this is the same as 3 times by 3 to the I times by 1/5 of 5 to the j. And this works out to be 3 over 5 lots of 3i times by 5 to the j. So this is actually 3/5 of n. But this isn't good because we want n to be greater than 2. So what can I do to this to make n greater than 2? No, sorry, that's not... what am I talking about? No, n is greater than 2. But I want to find the next... Okay, so for some n, I want to find the next charming number. Yeah, so I'm looking for a quantity that's bigger than n. So that's not particularly good. And ideally, I want it to be smaller than 2n. The reason for that is because if I can prove that I can write any number of the form n plus a as a charming number, as a sum of unique charming numbers, then if I can prove that there's another charming number below that, then I should be fine. So maybe I don't want 1. Well, if I increase the 5, that would just, if I increase that to a 0, that would just be 3n. That would be too big. So I think what I'm going to do is I'm going to make this to a 2. Because then that would be 3 squared. So then that will actually become 9/5 of n, which is actually bigger than n but smaller than 2n. So for any particular n, there must exist another charming number that's between n and 2n. And it's 9/5 of n. That's good. But then what if I is not 0, something else? Let's switch it around. Let's say not I. Let's say I was actually greater than or equal to 1 this time. And now geez. And let's say the j was 0. Then I'm going to consider, would the same thing work? So I've now got 3 to the I minus 1 times by 5 to the j plus 2. Would I need to go that far? I don't think so. I think I could just have it to the j, couldn't I? No. Yeah, I think I'd need a plus 1. Yeah, because then this becomes 1/3 of 3 to the I times by 5, lots of 5 to the j, which is actually 5/3 of 3 to the I times 5 to the j. And again, 5/3 of n, which and this is n. This is between 2n and n. So in actual fact, it doesn't matter if the j is 0 or the I is 0. There's always going to be an n value between just under double and that. So now I can just, I can just do this. So by induction, let n equal to 3. This is what's called my base case. And when n equals to 3, then I've got 1 equals 1, 2 equals 2, and 3 equals 3. These are unique, charming numbers. So this works. Okay. Yeah, and by doing this, actually, I've shown that the first 3 can be written as charming numbers. And then if I can show that up to double of that 3, which is 6, there's a charming number between 3 and 6. There might be more than one. It's not unique. There might be 2. I mean, there's this whole 9/5 n and 5/3 n. Sorry, 9/5? Yeah, 9/5 n. You know, it just depends. And then the point is this block can be written out by induction. This follows that subsequent blocks can be written as unique sums of charming numbers. Yeah. So if I can prove that one block can be written like that, then that should be fine. And then it carries on for the next one, because then I know that for some arbitrary amount, yeah, so hold on. This stuff proves this assumption. As in, for any charming number I find, there's always to be another charming number that's less than double that number away. That's fine, doesn't matter for some arbitrary I and j. And if I can also prove that all of the numbers leading up to that initial set, or an arbitrary set, are the sum of charming numbers, then the next set up to double will be okay as well, because now I can just add arbitrary amounts of these things to get to the next one. For example, I can add 3 and 1 to make the 4, I can add the 3 and 2 to make the 5. And then because I don't need to add 3 to itself to get the double, I know I've got another charming number to play with there. So yeah, that's fine. Yeah, oh man, so I've got an hour and 40 left. Yeah man, this stuff's difficult. You'd have a lot more time to check your answers, write out better notes than this. But yeah man, just working through these things, looking at video solutions. There must be tons online, and actually on the BMO website. Yeah, it's just really worth it. So yeah guys, hope you found that interesting. Toodaloo.